Cowabunga, everybody. Welcome back. Alright, so in this video today we're going to be looking at periodic motion. What is periodic motion and what kinds of things can we learn about using periodic motion? Alright, so let's start with just the basic definition. Periodic motion is any motion that repeats itself at regular intervals. Some examples are the Earth, right? Every 24 hours we're going to start a new rotation on our axis. Every year, every 365 days, we're going to start a new trip around the sun, right? That same path is going to repeat itself at regular intervals. We know it, we can time it. It's simple, it's easy, right? Look at a clock, right? Every 60 seconds, the second hand goes around. Every 60 minutes, the minute hand goes all the way around. Every 12 hours, the hour hand goes back around, right? These are things that repeat themselves at regular intervals. Okay? Now, the things we're going to be focusing on are going to be pendulums and springs. All right? So those are two things that can undergo simple harmonic motion that we're going to kind of focus our attention on. All right? But before we get there, what we've got to do is take a look at some key definitions for periodic motion. All right? Let's start with period. Okay, the period is the time it takes to complete one cycle. All right, so if you're a pendulum, for example, right, and you start out here, one cycle would be over here and then back. That's one cycle. And the amount of time that that took, that is the period. It's measured in seconds. The frequency, on the other hand, is the number of cycles in 1 second. All right, so a number of cycles per second, that's why it says per second. Right, that's measured in hertz. So in other words, how many times does it complete one full cycle in a second? All right? And finally, we have the amplitude. That's the max displacement from equilibrium. I couldn't fit it, but that's measured in meters, right? It's displacement, it's meters. Okay? So these are some key definitions to help understand how we can measure and quantify periodic motion. All right, cool. So let's start with a pendulum. Oh, before I get to that, let me just say period and frequency are reciprocals of one another. So you find the period by taking the reciprocal of frequency. Right? So period, capital T, is 1 over the frequency. Right? Simple as that. Okay, now, what we're going to be looking at mostly is how do we calculate the period of a pendulum or period of a spring? Okay, well, let's take a look. Okay, here is the basic equation. Now I'll show you the equation, then we're going to talk about it just briefly. Okay, so we have a period of a pendulum, a little sub t, so that way I know I'm talking about a pendulum, equals 2 pi times the square root of L over G. L being the length of the pendulum and G being your local acceleration due to gravity, right? So a period or a pendulum with a length of 1 meter will have a different period on Earth than it will, say, the moon. All right, so period measured in seconds, right? If you were to do some dimensional analysis to figure out, you do end up getting seconds, so that's good there. Now this 2 pi part is interesting, right? It doesn't add anything to the units, so why have it? Well, think back to math for a second. When you do one full trip around your unit circle, you say you've completed 2 pi radians, right? That's kind of what this is representing here, right? That 2 pi represents a full trip, right? So that's how we know we're talking about a period, not some just time, okay? So, interesting to note here, kind of more talking about the physics behind this, is it's just the length, right? It's not how far up it's swung, it's not its amplitude, it's not the amount of mass on the bob, which is just whatever the thing on the end of the pendulum is called. It's the length. You have different lengths, you'll have different periods. 2 pendulums with the exact same length from the contact point or the pivot point to the center of mass of the object, that will change, or that will affect its period. Right? It doesn't matter what mass is at the bottom. You can have 100 pounds versus a pound. The pendulum's period is going to be the same. Okay? Neat, huh? I think so, if I were to just say so myself. Now, let's look at a spring. T sub s equals 2 pi times the square root of m over k. Alrighty. So we have the period of a spring equals 2 pi. There's that 2 pi again to represent one full cycle. Which means if the spring starts out here, goes here, and then comes back, that's your one full cycle. Right? Equals the square root of m for mass over k, your spring constant. So in this case, yes, the mass on the spring does affect how much time it takes to complete one cycle. And here k is your spring constant. If you think back to elastic potential energy, that k, that spring constant, represents how stiff the spring is. So a higher k yields a higher spring constant. Okay, let me just make sure I'm not missing anything here by checking my notes. And looks like I covered everything I needed to cover for this. So I think we're good. So key things here are, when measuring period, it's always from where it started back to where it started. All right. That 2 pi in the equation is just there to represent that full cycle. Pendulums are only affected by its length and the acceleration due to gravity. Springs are only affected by the mass and the spring constant. All right, so mass does not affect pendulums, and length does not affect springs. All right, so with that, see you later.